Now, if we haven't got Kenyon, maybe we should move to the second speaker, just in case he arrives later. Okay, that's great, Charlotte.
Yeah, I'm Charlotte. So,
would you be happy to start first instead of second?
Okay.
Okay, great.
All right.
Okay, thanks very much.
So, can I start now?
Yeah. It's
Let me share the screen first.
Very good. So it's Xiaolong Liu presenting a paper, joint work with Philippe Baynard and Sylvie Dutra on inducing inference relations from inconsistency measures. Okay. Thanks very much.
Okay. Can everyone see the screen now?
I can. Can everyone in the audience see the screen okay? Oh yeah, well you can. Yes. You can do it.
Okay.
The virtual as well. Yeah.
Okay. Hello everyone. I'm Xiaolong Liu. It's a pleasure to be here to present my work. I'm a PhD student of Sun Yat-sen University and also a resident student of ERIT. And today I present work also with Philippe and Sylvie. And the title is Inducing Inference Relation from Inconsistency Measures, as the chair has introduced. My presentation is organized as follows. So I will first explain why we introduce. I will first explain why we introduce a new family of inference relation by using the function called inconsistency measures, which are formally introduced in section 2. Then section 3 shows how we define these inference relations, and section 4 and 5 respectively investigate whether they satisfy the so-called Kelvin properties and pair consistency. Then section 6 studies dependencies and incompatibilities between rationality postulates of inconsistency measures, and at last we conclude our work and point out to future directions. So the motivation of this paper is to draw valuable information from inconsistent knowledge bases, more specifically, to draw a non-trivial inference relation from inconsistent knowledge base by taking advantage of inconsistency measures, which are just functions measuring the degree of inconsistency of bases. And although many inconsistency measures have been proposed in the existing literature, but a few are based on them, except Benson Brown's work. But a drawback of his work is that his approach is restricted to particular inconsistency measures. So it would be desirable to find an approach that works for a broader set of inconsistent measures to the best of our knowledge. No such general approach exists. However, in our paper, we will give a general approach to define inference relation induced by inconsistency measures. As I have mentioned, an inconsistency measure is just a function measuring the degree of inconsistency of a large base. And the higher the value, the more inconsistent the large base. For example, the drastic measure ID states that the value is 0 if a knowledge base K is consistent, and otherwise the value is 1. Another one called another inconsistent measure, IMI, measures the number of minimal inconsistent subsets of a knowledge base. And the greater the number of such subsets in the knowledge base, the more inconsistent the knowledge base. And rationality postulates of inconsistent measure can give general guidelines on how inconsistency measures should behave in some scenarios. For instance, a free formula for a knowledge base is a formula consistent with all consistent subsets of that base. Then the postulate called free formula independence requires that adding a free formula to a knowledge base should not change the inconsistency degree of that base. Another one called penalty requires that if a free formula for a knowledge base does not belong to that base, then adding that formula to that base should increase the inconsistency degree. Now we are ready to induce inference relations from inconsistency measures. Our idea is to investigate what happened under an inconsistency measure when supplementing the knowledge base with the negation of a formula. And if the measure assigns a greater inconsistency value to the knowledge base supplemented with the negation of the formula than to the knowledge base itself, then it means somehow that the knowledge base infers the formula. And regarding such a expected behavior also as a sufficient condition, a notion of an induced inference relation appears. That is definition 4. It's worth mentioning that every inconsistent measure induces an inference relation. To better understand this definition, consider this example 5. So given a consistent knowledge base K, where A and B are just items, so and this inference relation is induced by IMI, which measure the number of minimal inconsistent subsets. Then B can be inferred from K, since adding B to K generates 2 minimal inconsistent subsets, while K has just one minimal inconsistent subset. So that's our idea. And an important property of the newly defined inference relation is that for any consistent premise, these inference relations are equivalent to the classical inference relation. Then next, we will further study the newly defined inference relations, more specifically, under what rationality postulates of an inconsistency measure, the inference relation induced by that measure can satisfy the so-called Kähler properties, which are non-monotonical properties proposed by Kraus-Lehmann-Mogillo in this paper. And here are the Kähler properties investigated in our paper. But due to a limit of time, we only introduced 2 positive results and 1 negative result. And this proposition tells us a result about reflexivity. That is, as long as the inconsistent measure satisfies its penalty, then the induced inference relation will allows any consistent formula in a knowledge base K to be derived from K. And we argue that this is the best result we can get about reflexivity, because no one expects inconsistent formula in that base to be inferred. For example, for this inconsistent K, and the conjunction of A and not A cannot be inferred from K. So here is another result about rank weakening and dominance. Dominance says that substituting a consistent formula by a weak one should not increase the inconsistency value. Well, Attribution increases that adding the inconsistent formula would increase the inconsistency value. Then this proposition states if an inconsistency measure satisfies these two postulates, then the induced inference relation satisfies a restricted version of rank weakening. So we also have a negative result. That is, it's difficult for an induced inference relation to satisfy property OR, because it's a delicate matter to measure disjunctive formula, and there are few postulates about disjunctive formula in the literature, except disjunction minimality and disjunction maximality. And however, we found that even if a consistency measure satisfy these two postulates, it's still very difficult to satisfy property OR. In other words, we fail to get a general result. Next, we check if the induced inference relation are paraconsistent. That is to check if some formula cannot be inferred from an inconsistent knowledge base. And compared with the original paraconsistency, we require that for any inconsistent knowledge base, there exists some formula that cannot be inferred from that base. So it's a stronger definition than the original one. Then we have proved that if inconsistency measure satisfies its free formula independence, the induced inference relation must be paraconsistent. There are similar results for the following postulates. I mean that the induced inference relation is paraconsistent if an inconsistency measure enjoys this property. All right, and here is a result concerning relative inconsistency measures. Researchers have proposed numerous inconsistency measures, which can be divided into two categories, absolute measures and relative measures. The former one gives total amount of inconsistency in the knowledge base, while the latter computes the proportion of the base that is inconsistent. We have shown that every relative inconsistency measure can induce a paraconsistent inference relation. Okay, 5 minutes. And since we proposed some new rationality postulates in this paper, so we have shown some dependencies and incompatibilities between these postulates. For example, MI separability entails an telomere increase and tautology independence. And here is another negative result. That is, if I satisfy penalty and the tautology line increase, then the induced inference will fail to satisfy end. And at last, we conclude our work. So we have proposed a general approach to define a new family of inference relation by using inconsistency measure. Then we have checked whether they satisfy Killing properties and whether they are paraconsistent. And in our future work, we will extend finite premises to infinite premises. That is, use infinite knowledge base as the premise of the inference relation. And the other idea is that to apply a more apply the strict pair consistency. The idea is that if an inference relation satisfies the strict pair consistency, then the premise and the conclusion share variance. In other words, premise and the conclusions are relevant. Okay, that's it. Thank you. And any question are welcome. Okay.
Question from Nico.
So I think this is a really nice application of inconsistency measures. So could you go back to the initial definition where you defined phi follows when the inconsistency adding not phi is greater than something?
You mean the definition?
Yeah, the very basic definition. Ah, yes, exactly. So I was wondering, I haven't thought about it a lot, of course, but I was wondering when I saw this, why do you consider set minus on the right-hand side? Couldn't you also consider the union again? So say K union not phi is more inconsistent than K union. Ah, no, it's something else. No, what I was wondering is if you go back to this definition, couldn't you also consider K union not phi versus K union phi, or does that not make sense?
We just need to take care of the special case that not phi is when not phi is in K. So that's we need the malus.
Yeah, I see that this is one way, but does the other way make sense or not? This is, or maybe it's, I don't know. So when I first saw this, I thought perhaps you could consider something like K union not phi is more inconsistent than K union phi, or does that not make sense? I'm not sure.
Yeah, at first we have the same doubts, but at last we adopt this definition. That's why we need set malus and the union. Yeah, and yeah, we will try maybe there another way to do this. Okay, maybe in our future work. Let's see.
Oh yeah, right.
Thank you. Thank you. Question.
Do we have a question for that?
Yes. Yeah. Well, I have one question, which just because the last before lunch there was a lecture by Laura Giordano. Her name, the title was On the KLM Properties and for the DL. I wonder whether this KLM properties by her and the KLM properties discussed by you is the same, or it's just coincidence of the same abbreviation. I don't know whether you listen to her.
I think they are the same. Yeah.
The same.
It's the same thing being referred to.
Yeah. It's the same.
Okay, thank you.
Tony?
There are a lot of paraconsistent logics that have been defined in the literature. Are there any advantages of your proposal over any of the well-known paraconsistent logics?
Yeah, as I've mentioned in the last page, in our future work, in this paper, we have defined a strong paraconsistency than the original one, and actually we also have shown that the strict paraconsistency, if an inference relation satisfies strict paraconsistency, then can guarantee the relevance of a premise and conclusions. I think that's, and we also have shown that this if a inconsistency satisfies these postulates, then the induced inference relation will also be strictly paraconsistent. I think that's our advantage. We will show in our future work.
But how does that relate to existing paraconsistent logic? So, for example, Belknap's four-valued logic, or some of these paraconsistent logics from Brazil, for example.
We can just to require that so in our future work, the definition of paraconsistency would be some substitution of phi cannot be inferred from K. That's the underlying idea of strict paraconsistency.
Right.
I don't know whether it's answer your question or not.
Maybe we could talk offline.
Yeah, maybe we can talk about it later.
Okay.
Yeah.
Okay, thanks very much again. That would be all right, Ramon. There's a close-up of you, Tony, on the big screen at the moment, just to let you know. Oh, it's gone now, unfortunately.
This one. Okay. So my talk is about merging. So merging some kind of special abstract entities. We call that epistemic states. So the motivations many years ago, more than 20 years ago, with my colleague Sebastian Konieczny, we have defined some kind of operation we call belief merging. The goal is to extract information from say, several sources of information, coherent information, and we state some rationality axioms. And in that setting, the information is represented by propositional form. And at that moment, many years ago, David Mackinson said, oh, but it is very similar to problems in social choice theory. And yes, it's similar. After that, we show some representation theory. And that's look very similar, but the links, very similar to social choice, but the links, the real links was not on the table. So many years after that, in 2017, with my colleague Amilcar Matadias, we established more links, but we need to represent the information in a more complex form. We call this epistemic state. It's an abstract form. You will see that. And that allows to have really real links with social choice and to formulate social postulates. That is interesting. At that time, we begin some research about impossibility theorems, and we established one theorem. The topic of this presentation, this research here, is to continue this program to establish links with social choice theory, merging these entities, complex entities, with some manipulability. So, look at this example. See, this is an example to understand why it's interesting to have more complex information. So, Anne and Bob have to travel from point A to B, and there are 4 paths to accomplish the travel. W1, W2, 3, and 4. And thinks that the best way to carry out the travel is W1. And after thinks that WI is better than WI. Okay? Both thinks that the best way to travel is through the path W4. And the other possibilities are equally good. A common consensual result in this situation is to take path W1, okay? The path that Anne prefers and which is not so bad for Bob. Whereas path W4 is very far from Anne's preferred path. Indeed, the consensual preference is path W1 as the first option, then path W2, the last option are in different paths. So there's no really. So now suppose that Anne and Bob have hate heavy traffic. The last news about the traffic informed that there is an enormous traffic jam in the path W1, whereas on path, the other paths there is a normal traffic. With this new information, which can play the role of integrity constraint, the global preference should be path W2 as the first option. The second option is path W1. So let me represent that like preference, like here. So the most preferred path for Anne is this, and then this, and then this, and so on. For Bob is this, the most preferred path, and this is equal for him. And if you take scoring here, the sum of these ranks, the global preference for these two is this one, okay? So in that case, so the most preferred, the global is this one. Now, this is the information about the traffic. So I put this, the jam is here, this is normal. So if you make the lexicographical mixture of this information is very important. And this, you obtain this total preorder, and in this case, the most preferred path, the indicated path is this one, okay? So the problem is that with only propositional logic, you can have this kind of gradual representation. However, with logic, you can point to the preferred, this if these are models, interpretation, you can point to this preferred on the top of this preference. Okay, that is the point. After I will show you how you can manipulate this. What means manipulate this kind of information? Okay, what does mean that one agent can manipulate this? Okay. Okay. So the abstract notion of epistemic states is a very formal. It's a set. It's a triple. Here. Oh. Here. You have a triple. You get this triple. You call this triple epistemic space. The important thing is that is a set. B is a function sending the element of this set in logical formulas. Okay. Consistent logical formulas. B. Okay. And B allows us to identify the belief of the epistemic state. Okay. The way to think the example. There are two very simple examples to think epistemic states. The more simple way, the more perhaps interesting way, is to think that epistemic states are total priorities over interpretations. Okay, and the belief are the formulas. For instance, if I take this epistemic state, the belief of this is the formula having this interpretation as the only model. Okay? That is one way, one concrete representation. Another concrete representation are the propositional formulas by, okay, you take a formula and the belief is that formula. That's all. It's the identity. Okay? But there are other representation, ranking functions, conditionals. That is the important point. There is a very concretizations of this notion. So with this notion of epistemic states, you can perform belief merging. So the point is you have profiles, and you need to extract here. The point is you have profiles. You have the index are agents, okay? And the point is how to extract coherent information from a profile, and in the case where you have the point is the input of the operators are profiles and epistemic states, and the output is also an epistemic state. So at this level, all the information is of the same type. That is important. So you have some rational properties for these operators, which are formulated only in logical terms with the help of the belief function. The belief function is a function which transforms an epistemic state on a logical form. That is the point. So you can use logic with B of the epistemic state. The point, I pass the details about rational postulate, is this is the important point. The postulate allows a representation in terms of some ordered structures. Okay, so the belief of the output here, this is the operator. This is the input, a profile, an epistemic state, and the belief of the output is in fact the models of the belief. This means the models are the best interpretations of pre-order, global pre-order associated to the profile. And this is the belief of the integrity restrictions, the integrity constraints here. Okay? So that is the important point, and that make a real link with social choice. This is the kind of thing you can see. Why? Because if you want an operator like that, you need only to have this. Of course, you need to have a concrete representation, but you need to establish which is this with some properties. Yes, you need some properties of the behavior of the construction of these total preorders. Okay? So the point is, what is manipulate here? I pass the details, I give you an example. So the first line here is the first example of Bob and preference about the travel. And here, Bob changes his preference, and at the end, the output is this one. So the preference of Anne are the same, but here Bob say mispreference. No, the real preference are that, and he changed here. And at the end, the most preferred path is this one, and this is in the real preference of Bob is the preference, and in this real output, W4 is here. Is not the best. So, saying a lie, he obtained a best result. That is manipulate. So I say a preference which is not my real preference, and I obtain a best result. Okay? So the work here is to establish social postulate and say that which operators can be manipulated. So the formalization of rational social postulates are in logical terms. So and the result here is that some operators satisfying social postulates, these two postulates in particular here are manipulable or dictatorial. Dictatorial means that there is one agent that imposed his preference. Okay, so it's duality, but the techniques are in the paper and the definition of rational postulates. The important point is this to pass to this complex representation, allows to have a general result of impossibility and manipulation. Okay. What is important too is that well, the kind of representations used say that you can look for more general order structures because here we consider only total preorders in the representation. So changing some postulates, you can, we guess, we can have some representation of more general structures. Okay? That is, okay, I'll stop here. Sorry.
Thanks very much. Do you have any questions? No?
No, over there. Clearly.
Oh, sorry, they suddenly appeared, or at least I missed them a couple of minutes ago. Let's see who they are. Can you see who they are? Or was that just clapping?
Yeah, it was. Well, maybe it was clapping. No,
maybe.
not the...
Yeah, I think they've disappeared. So, did you want to ask something, Milan? Or?
No.
Something I was wondering about is that in the first example, you've got the sort of the +1 by one agent being sort of cancelled by +1 from the other agent. You know, in the Anne and Bob, you with W4 and W3 you end up at the same level because there's a difference of 1 between the two. So it feels to me that the inputs aren't really total preorders in this. What they are is numerical. They're numbers because you're adding them effectively, or they're cancelling each other out. So the representation, the input is really 1, 2, 3, 4, or 1, 1, 3, 4, for example. Fundamentally they're not ordinal. They're numerical.
No. Here is one standard way to put values, put ranks to the total preorders. So the input are total preorders, and then you put the most natural ranks in this way.
I suppose.
Sorry, for instance, suppose you have this the second here, okay?
Yeah.
And you have 3 levels.
Yeah.
All the rest of models and this.
Yeah.
Okay. So what is the rank here? Is the longs of the bigger descending chain. Okay. Here is 3. Okay. So it's a standard way, but you can represent with a rank given each agent. Can give you the rank of preference. Okay.
So I suppose the question is that could you, since these are effectively numerical anyway, could you extend it to being, because as it is, they're very particular numerical values that you're getting. You're 1, 2, 3, 4, or could you extend it to allow each agent a certain budget to spend? For example,
I think so.
And
yes, that is an interesting idea.
Yes. I suppose the problem.
If each agent, yes, I think so. And this is linked, I think so, with some perhaps here. This is in some sense the restriction. The integrity restriction, perhaps you can put this information.
Okay.
So about the budget in this in this input.
Thanks very much. Do we have any other questions, or otherwise we can move on to Christoph? Thanks very much. So for the next speaker is Christophe Labroche, who's going to be talking about explanation with the winter value, efficient computation for hierarchical Shapley inputs. And usual apologies about pronunciation of names.
Okay.
Thanks.
So, good morning, everyone. So I apologize for not being with you physically. So thank you, Nick, for the introduction. So this can you see the slides?
Yeah.
Yeah. Okay. Thank you. So we are talking about here about explanation. So it's a hot topic in AI. So it has many interests. First, for everything related to man-machine interactions. In order, when you have an operator in a system and you want to increase the trust and the acceptance of this user, and also for trustworthy AI, where you want to have a validation and qualification of an AI model, especially in safety critical systems. Looking at what are existing approaches in explanation, so we have at the bottom. So the first way to do it is to have what is called XAI by design. So it means that the model you have is directly explainable. For you can think of rules, for instance. Otherwise, you just do your model without any explanation consideration. But once your model is constructing or learned, if it is machine learning, so then you can again have two possibilities. The first one is to construct a proxy model, what that is called an explainator that is explainable. So, for instance, from a model generate rules or things like this. And the second one is to what is called model inspection is to deconstruct your model by making, for instance, sensitivity analysis or things like this. And what you're talking about here is in this area. So one of hot topic in AI, especially in machine learning, is feature attribution. So you have a model, you have inputs and outputs, and given the outputs, you want to know which inputs actually explain the outputs. So one way to do it is to compute a level of contribution of each feature of each inputs to the output. So it can be used, for instance, for user, or instead of showing all features of all attributes, you just show the one that has the highest value of attribution. So we consider here, given this introduction, a decision setting, decision model, where we have a set of attributes denoted by 1n. For each attribute in this list, you have a set which are all possible values for this attribute. Can be continuous or discrete, does not matter. And then we consider a set of alternatives which are in the Cartesian product of this attribute. So we consider a preference of a decision maker in terms of a utility function, for instance, can be a typically numerical values, like in your utility theory, where so for each element in this set of options, you give a score, so that a higher score means that it is preferred. So from this, you can make solve several problems, like selection of the best elements, or ranking elements from the best to the worst, or assigning a category to an element, and so on. For illustration, let's take an application for the supervision of a metro line, for instance. So here, attributes are key performance indicators. Let's say for supervision, you want to, for each day, let's say to supervise the quality of service of the train. For the concern of passengers. So passengers are concerned with how many canceled trains they can have, and also for regular train, for the punctuality of the train with respect to the time schedule, and also regularity, the time between two successive trains. So we have these three metrics, okay? But then imagine you have a large city where you have several metro lines, and so we organize actually, we compute these three metrics, not you don't make just a simple average over all situations, but you have segments. So we distinguish peak hour versus off-peak hour. And for peak hour, for instance, let's say there's three segments of a metro line. So we compute these metrics separately for each segment. And then for each type of hour on each type of segment, we compute these three metrics. So on overall, you have 18 elementary criteria. So just an illustration, but you see that in a real application, you can have really a huge number of metrics like this. So for instance, if you have a degradation of quality of service, it's very helpful to have a system like we are going to show in order to pinpoint among all KPIs which one are responsible of the degradation of the overall quality of service. That's basically the application. So we are going to use decision model. So what we see here is it's organized in a hierarchical way. The point is each node in this hierarchy is explainable. For instance, this one is performance over a day, over the peak hours, the rush hour. This one is for the rush hour for the second segment, and so on. So it's not latent variables or latent nodes. It's something that a supervisor can really understand. So it makes sense to use such hierarchy, right? So we are going to have a model which is a decision model which is hierarchical. So it takes benefit of this hierarchy. On each node in the hierarchy, you are going to apply an aggregation function. Here it's a function that is able to model interacting criteria. So it's the technical name, it's a Schottky integral. I will explain in a second. And so we want to compute if you have, for instance, the degradation of the overall score for the root of this tree to have a computation of the influence of each node in this hierarchy. So I will explain, let's say, something which is pretty well known in game theory, but also now pretty used also in machine learning, which is Shapley values, and what we don't use that, and we use actually, and we justify it, an extension which is winter value. Okay, so let's take a very simple example, a flat example. And we see even for a very simple example, it's not so trivial. So it takes a simple function of three variables with this formula. It's a combination of min-max. Okay, it has been learned, let's say, or elicited by standard, let's say, decision elicitation techniques. And we want to explain why, for instance, an option X, which is quite bad, is less preferred than the best possible option with one everywhere. Okay, but okay, of course, Y is preferred to X because it's monotone over each attribute, and X is lower than Y over each attribute. But now the question is, which attribute mostly explains this difference? Is it come from the first, the second, or the third one? So if you want to just use simple methods, you are going to have some difficulties because basically attributes are not independent, and there are interaction among them because of these min-max functions. So one idea to use it is to isolate the contribution of each attribute. So how to do it? So you have this point where you are bad, you have 0 everywhere. So it is, let's say, the reference point. The ideal situations is Y. So you have a good value everywhere. Okay, we want to explain this difference. First, we are going to create an option where you move value, you change the value of first attribute from X to Y, and we keep the second and third values. We take this, okay, we have this difference of score. We go from 0 to 1 by this change, elementary change. We change the second variables and we change the third variables. Here we have the contribution of the third, and then the contribution of the second, which 4, and the contribution of the third, which is 2, just by making the difference in this chain. You might say, okay, it's nice, but it's arbitrary, because why did you choose this ordering first variables and the second one, and last the third one? So you could say, okay, let's try another ordering. You first modify the third variable, and then the second one, and then the first one, and so on. So the idea is to do it, but to average, so to make this computation over all possible ordering of the variables, and to average over all orderings. So it's a combinatorial formula, so we can write it in more compact way using a sum of a subset with these combinatorial things. And this is exactly the Shapley value known in cooperative game theory, where V is a transferable utility game, and here V corresponds to the score of an option which is equal to Y on coalition S onto the reference value X on the remaining criteria. And you can just subtract a reference value, but does not really matter, in fact. So, and if you apply it to our examples, these are all possible orderings. For each ordering, we have a vector of assignments to each attribute, and we just average, and you get this. And in this case, for instance, the third and the last one are the most impactful attributes. Okay, so now why would we need something else for our application, for our problem? The problem comes from the hierarchy. So let's take an example with this tree, where you have 3 attributes organized. So you have 1, 2, which are combined here, and the result is combined with the third one. So we make a similarity with gloves. So for the first aggregation, we take an OR operator, or a max if it's numerical, and for the second one, we make a hand operator or mean operator if it is numerical. What does it mean? It's on top, you want to have a score 1 if you have at least 1 left hand glove and 1 right hand glove, which means that we should have attribute 1 on 3, or attribute 2 on 3, or all attributes present to have a pair of gloves, so to be happy in some sense. So what happens if you apply the Shapley value to this in order to see what is the contribution of each glove? What you get is gloves, the left-handed glove, so 1, 2, gets 1, 6, and the right-hand glove takes 2/3. Does it seem fair to you? Actually, you somehow to have a pair of gloves, you can say the left or the right parts are symmetric, so there's no does not make sense to have a higher value, to assign a higher value to the left or the right. So so this 2/3 value seems overestimated here. So what happens if you actually say, okay, let's the 2 left gloves are quite unhappy and they form a coalition. So they form a new player that we call 1, 2 together. And if you apply the Shapley value on this new game where you have only 2 players, a coalition 1, 2, and 3 alone, then we will get that both players will get 1/2. So you see that just making player 1, 2 form a coalition makes the value for the last player be lower, coming from 2/3 to 1/2. So this problem is known in cooperative game theory. That's the O1 value that makes this, and so the winter value is an extension of this to any coalitions, to any hierarchy of players of criteria. The basic idea is when you come to this combinatorial formula, actually, you are going to not sum over any permutations, but restrict to the permutation which are consistent with respect to your hierarchy. Okay. So the technical formula of this, the extended Shapley value, so the winter value on trees. So you have a tree like this. Imagine you want to compute the influence of the leaf number 1, so this one. So you draw the critical path from the root to this node. So it is a red path here. And we consider all nodes at distance 1 to this. So these are all nodes with a green edge. So we have a green edge vertices number 2, 10, and 14. And actually, when you compute this winter value, you don't care about what's below these nodes. For instance, below node number 14, whatever the organization below, whether you have a complex hierarchy like this, or even a different where you will organize this node differently, or whether 14 is the leaf, you will get the same results. So the idea is to cut the tree. So you go from this one to this one, just cut the subtrees below these nodes at distance 1 to the critical path. And this already reduces a lot the combinatorics. So and the formula goes like this. So at the end, you have your chain from the leaf you want to explain to the root. And you have some at each node in this path, you have some children. So for the root, you have R1 in this critical path, but also nodes, and all these nodes are denoted by N1, and N1 prime is N1 without R1, and so on. On this winter value is simply the Shapley value. It's some kind of recursive Shapley value, where you have a Shapley value at these levels combined with the Shapley value at the next level, and so on. So you have the sum of all subsets in each of these layers. So you have a multiplication of the coefficients. It's exactly the coefficient you will get for the Shapley value, except it's just you have this for all layers. So you see it's somehow a nested Shapley value, just simple as this. Okay, formula looks complex, but it's just that simple. Now our model, what does it look like? It's as in the example I show. I can't see how many times.
It's so you obviously didn't see my messages. It's actually you're pretty well out of time now, but if you could try and finish up in the next couple of minutes.
Yeah. Okay. Yeah. So it's a combination of min max, but it can be written as a linear combination of min. On the basic idea is the Shapley value or the winter value are linear with respect to the model, and because you have minimum functions, you have minimum function, we can prove the model. Okay, let's take an example. So the overall quality of service, let's say it's a weighted sum at the top level, and then you have a minimum for peak hour. It's the worst case among 3 segments. On here you have another formula. Okay, we want to understand what is the influence of all these parameters when we compare an option Y and an option X. On the basic idea, if you want to compute this at the top level, okay. So the influence comparing X and Y, what is the influence of this node P? So we have the critical path when we cut outside. At the top level, because top level is the weighted sum of the peak and off peak, and because the winter is linear, we have something which is as simple as the influence of this of the leaf with respect to this node. So we have one term below. So we don't have to sum over this. Okay, so we win some time. Now at the next level, it's the formula. It's basically you have a mean over M1, M2, and 3. The basic idea here is because you have a minimum, you see that the value of M3 is very large. Okay, it's always larger than the value of M1. So this means that the value of whatever the value of M3 you take for X and Y, it does not influence. So you can get rid of these three M3 nodes. So instead of summing over all subset of M2, M3, you just have to sum over a subset of M2. So again, you reduce the combinatorial. And then when you are here, you now take the two possibilities over M2, so it can be the value of X or Y. But for the value of X, when you fix the value of M2 to X, you see that the value of X over M2 is lower than the value of M1. So the influence of changing the value of P is 0. So this means that this term is 0. So very easily you can check this. It's like a pruning in branch and bound. And so there remains only one term. And for these terms, now we go to the last sum over the last layer. So you have to sum over all subset of this on these two nodes, and you can easily check by the same reasoning as before. Then the value on CT cannot be Y, because if you assign value of Y at CT, the score will be always lower. So you get again a contribution 0. So you remove again one term. Okay. So this remains only the value of X on C2. And when you finally have explicit formula, we get the results. So from this, actually, we can derive an algorithm which just generation of this. So you see this kind of idea of branch and bound. And we have an experiment where we compare the efficiency of this pruning compared to the regular formula with no pruning. So you have good results, and that's it. Thank you for your attention.
Do we have any questions, Milan?
Okay. So your interpretation of this winter value was that it is a kind of generalization of Shapley value from cooperative game theory. As far as I know, this Shapley value for this supermodal or convex games, so it somehow this corresponds to extreme race of certain extreme points or vertices of certain polygon, which is called core. I wonder whether this winter value has also some interpretation in terms of polyhedral geometry.
Yes. So yes, I see what you mean. So when you have the core when the game is convex, and the Shapley value is the center of gravity of your core or something like this. Actually, this concept of extended Shapley value on cohesion of super, let's say, cohesion structure is not so well studied for other concepts than Shapley value. So it should be extended to core or even other concepts like nucleolus or whatever. So I cannot answer you because. But what we what we saw at least is one, and that's a result that if you learn a general model on you take the linear. I mean, if you take a general game on the closest linear models, is the one that has the in the sense of standard of root mean square is as a coefficient the Shapley values, something that is known. We actually have seen in experiments, at least, that this is true also for hierarchical models. So you have some properties that is known in game theory that are also known in these hierarchical models, but it's an interesting question. And there's also some new works to do to continue this comparison between different concepts. Yes.
Thank you. Any further question, either from online people or here? Just one general question, Christoph. You've got a lot of experience at working in multi-criteria problems. Is this quite a common situation where you have these hierarchical criteria?
Actually, in a high many times people are using attribute in a flat way. It can be in machine learning or in preference learning, but in decision aid, we always come up with something like this. It's for the problem is when you have a real decision maker, and you want to explain the results. If you have just a flat model, you have the attribute on the top, the overall results, and nothing in between. So it makes sense to have these intermediate nodes, to have a simpler communication with the decision maker and explain things. And also for the elicitation, it's also simpler. So it depends on the community, but in the decision aid community, it's quite usual, I would say.
Okay. Thanks very much. Yeah. Thanks again.